So today's lesson, we're going to look at the Fohn effect. So the air mass we're going to be looking at is tropical maritime. It's a common air mass, affects us about 25% of the time, but we need to think about its source initially. So its source is about 30 degrees north off the coast of Africa. It's got that dominating high pressure, if you remember from our Hadley cells. So the temperature is going to be very warm. If we think about its humidity, we know if the air is warmer, it can hold more moisture. It's sitting over that sea, so it's picking a lot of moisture up, so we know it's going to be warm and humid. Because it's being heated from the surface, we also know in that area it's going to be unstable. But as it moves towards us, or north towards the UK, it's been affected, it's going to cool down, so it's been affected by that cooler surface as it moves north. If it's being cooled down, therefore its temperature is going to be decreasing. Therefore, it's not going to be able to hold as much moisture as it cools down. If it's the air mass's temperature is also decreasing, it's going to be making it more stable. So as we look specifically into how it affects with the Fohn effect, we know from our stability lesson that the dry adiabatic lapse rate is 3 degrees per 1,000 foot. A saturated adiabatic lapse rate is 1.8 degrees per 1,000 foot, but for ease of maths, we're just going to use 1.5. As we build it up, we're going to have the air temperature and the dew point temperature together as well. So our tropical air mass has been moving towards us, cooling down, becoming more stable. And it will rise at a high ground with a temperature of 11 degrees and a dew point of 8. As it hits a hill, it's going to be forced up that orographic uplift, and it's going to start to cool. And we can see it's not reached its full saturation yet, so it's going to cool at that dry rate of 3 degrees per 1,000 foot. So at 1,000 foot, we're going to have a temperature of 8 degrees, and we can see now it's reached its dew point. It's fully saturated. It cannot hold any more moisture. So we're going to start getting that initial bit of our cloud forming. It's now going to cool at our saturated adiabatic lapse rate. So as it continues to climb to 2,000 foot, you can see we're going to have a temperature and a dew point now of 6.5 degrees. And our cloud continuing to form. Continues to rise. It's going to come down to 5 degrees temperature and dew point. As it's now cooled and we know it's stable, it's going to flow back down on the other side. We've also had, it's stratocumulus type of cloud, and we're going to have a lot of precipitation because it can't hold any more moisture, so it's raining, it's getting rid of its moisture. So as it now descends on the other side, we can see it's lost a lot of its moisture, and therefore it now becomes unsaturated again. So as it descends, it's now going to descend and increase its temperature at the DLAR, so 3 degrees per 1,000 foot. So you can see at 2,000 foot, our temperature is 8 degrees, and our dew point is stayed at 5. It continues to descend, we get 11 degrees and 5, and then back on the surface, 14 degrees and 5 for the dew point. So what we can effectively see here, on the leeward side, we've got a higher cloud base, because it's now got less moisture. It's warmer on the leeward side, and we've got a bigger gap between the temperature and the dew point. Our air is also going to be more stable, and that is the Fohn effect.